washing is not a new process. In the past, it has been practiced in crude carriers by various companies. Today, however, IMCO regulations make crude oil washing compulsory for all crude carriers above 20,000 tons, which do not have segregated ballast tanks. The reason for these regulations is to prevent pollution, both accidental and operational. The problem is caused by the sludge which settles out of crude oil during long voyages. It settles onto the bottoms and horizontal structures of the tanks. On completion of cargo discharge, most of this sludge remains on board. In the center tanks, about 80% remains on the bottom. In the wing tanks, it's only about 60%. The rest remains on the horizontal stringers and beams. Some even remains on the tank sides. If left to build up in the tanks, this sludge would cause serious drainage problems during discharge. In the early days, this sludge was discharged overboard by repeated water washing of the tanks on the ballast passage. The unpumpable residue was laboriously removed by hand. Eventually, the oil companies developed and put into practice load-on-top operations, which reduced the amount of oil and contaminated ballast water discharged overboard. Progressively, IMCO devised a number of stringent regulations limiting the amount of contaminated discharge permitted to a tiny fraction of what was once considered normal operational practice. These restrictions are undeniably good for the fishermen and the wildlife of the ocean. However, it means that today, every crude oil carrier without segregated ballast tanks must efficiently operate a crude oil washing system as well as load on top. With water washing, seen here in a test tank, it is the direct impact of the jet that breaks up the hydrocarbon sludge and flushes away the lighter elements. Crude oil has a solvent action on the sludge, which supplements the impact action and makes crude oil washing many times more effective than water washing. Thus, the heavier hydrocarbons, the basis of the sludge, are dissolved in the cargo and pumped ashore. This will mean better cargo outturns as well as less potential pollution. It also means much less manual desludging on the ballast passage. With some crudes, no desludging may be needed at all, although some manual descaling may still be required. There are two essential requirements for crude oil washing. Firstly, a fully operational inert gas system so that the tank atmosphere remains inert throughout washing. And secondly, fixed tank washing machines with fixed piping arrangements. These machines can be divided into two groups: the single nozzle type, like this programmable deck-mounted machine, and the twin nozzle type, like this unit designed for bottom mounting. Usually, they're driven by the oil flow acting on an impeller inside the machine. Some machines are driven by an air motor working from a compressed air line. Each type of machine is fully capable of doing its job, provided, of course, that the oil pressure at the nozzle is up to specification. Some single nozzle machines, like these, have detachable control boxes. However, all wash between previously set angles of the nozzle. In a typical program, the machine would wash from the top of the tank bulkhead down to the bottom. Then it would be reset to wash up to a 50-degree angle. But there are any number of possibilities, each depending on the tank structure and the kind of crude. Single nozzle machines have a throughput of 110 to 170 tons an hour of crude oil and have to be programmed each time they're used. Twin nozzle machines, on the other hand, cannot be programmed. They carry out the same 360-degree cycle both horizontally and vertically every time. Such a machine would have a throughput of anything between 50 to 150 tons of oil an hour. To understand the system on your ship, consult your ship's crude oil washing manual and tank shadow diagrams. IMCO regulations insist that there must be direct impingement of the jet on 90% of the horizontal and 85% of the vertical area of a tank. In general, washing machines are fitted to the deck head of the tank, but to fulfill IMCO requirements, it is sometimes necessary to fit bottom-mounted washing machines. Not only must the equipment fulfill IMCO design criteria, it must also have been tested in practice. Before a vessel is given a certificate of fitness to crude oil wash, personnel from classification societies will go into the tanks to check that the washing programs in the manual are effective. This practical test is crucial. Even if the design is up to specification with regard to shadow areas, a vessel will fail to gain its certificate if unacceptable quantities of sludge are found on inspection. Spot checks may be carried out at any time once a vessel has been certificated. Crude oil washing increases the workload and the time spent discharging. IMCO requires all vessels to have a crude oil washing manual. This contains washing programs which have met the requirements. Let's look at some of the things that need to be taken into consideration in drawing up a crude oil washing program. How many tanks should be washed at each discharge? IMCO regulations state that all tanks to be ballasted, not just departure ballast tanks, must be crude oil washed. In addition, a further 25% of the cargo capacity must be washed in rotation. Ideally, every tank would be washed every time it's discharged, but frequently there is not sufficient time. Berth availability and charter obligations make the time allowed alongside an important factor. Generally, washing programs fall somewhere between the ideal and the IMCO minimum. If a ship is preparing for dry dock, all tanks should of course be crude oil washed. Cargo pump capacity and the number of cargo pumps are important. With, say, 6 machines in a tank, each putting in 150 tons an hour and using eductors to take it out, a good portion of the discharge capacity will be used solely for crude oil washing. As a high percentage of washing takes place after a tank has been discharged, stripping capacity is crucial. IMCO specifies that the stripping system shall be capable of removing oil at a rate of 1.25 times the total throughput of all the tank cleaning machines to be operated simultaneously when washing the bottom of the cargo tanks. It is essential to ensure that the bottom of the tank is kept dry during the final phase of the bottom wash. The number of grades and types of crude must be considered. Different crudes have different sludge-generating properties. A light crude will normally need 1.5 cycles from each machine, whereas a heavy crude will need 2.5 or even 3. Multi-grade cargoes will mean different washing arrangements. Use of a light crude to wash a tank which contained a different crude must be approved by terminal staff. If a tank was not washed after a previous discharge, allowance must be made for a prolonged wash to remove previous residues. The number and type of washing machines must obviously be taken into consideration. The single nozzle type can be set for 2 or more stage washes, so washing can begin before discharge of the tank is complete. This leaves less work for the stripping system when bottom washing. With twin nozzle machines, having a constant 360-degree cycle, washing should only begin when the tank is nearly discharged. Otherwise, time and energy will be wasted in washing the surface of the cargo. The complexity of the IMCO regulations makes it essential to keep close to the established washing procedures as detailed in the crude oil washing manual, although variations are sometimes necessary due to the variety of conditions that can exist. Crude oil washing takes up time, adds to the fuel consumption, and increases the workload in port. Thus, it's essential not to overwash. Wash sufficiently to dissolve the sludge. Overwashing is a waste of resources and has no benefits. A crude oil washing system will mean even more pipework in the pump room, so it's worth labeling clearly the different pipes. One day, it may stop someone from making a mistake. A complete washing plan must be given to everyone who's involved in the cargo discharge. Shore staff will also need copies. Let us now turn to a crude oil washing operation involving a discharge of 125,000 tons of light crude in a terminal in northern Europe. The operation begins a long time before the vessel comes alongside. It starts with a message notifying the terminal of the intention to crude oil wash. Usually, a week or 10 days' notice is sufficient, but some terminals insist on 6 weeks advanced warning. At least 24 hours before entering the discharge port, the inert gas system is run up. This not only checks it thoroughly, but also provides a good opportunity to top up the pressure in the tanks. IMCO regulations insist that the tank atmospheres are maintained in a non-flammable condition at all times. The oxygen analyzer in the scrubber house must be checked electrically. Then, the instrument is zeroed with nitrogen and then spanned using air. The reliability of this analyzer is crucial to the inert gas system, so make sure that it's correctly adjusted and operational. The portable oxygen analyzers must also be checked at this time. Zero and span them in a similar way to the fixed analyzer. By now, the discharge plan and washing program have been drawn up. The next step is to pressurize the crude oil washing line. Should the crude oil washing line have a water heating system, it is vital that these lines are now blanked off. A check is made to ensure that all valves to the washing machines are shut. A stripping pump is used to pressurize the crude oil washing delivery line. It is run up slowly to reduce the risk of hydraulic shock at the ends of the lines. Make sure that the air is released at the ends of the lines and the pressure maintained so that the line is pressured with oil and not air. A pressure gauge on the end of the delivery line will give a true indication of the working pressure of the system. When the system is up to pressure, the line is checked and any leaks discovered are made good. Once this is complete, the machine control units can be put in place. By the time the pilots come on board, the IG system and the crude oil washing line checks must be completed. As soon as the ship is berthed, the terminal staff come on board. They need to see the discharge plan and the crude oil washing program. Agreement must be reached on terminal regulations, communications, and crude oil washing abort procedures. A communications link is set up with the officers on deck and the cargo control room. Everyone must check that they understand their responsibilities during the discharge and washing operations. If anyone is in any doubt, ask the officer in charge before the discharge begins. Now the inert gas system is started. As the cargo pumps are not yet running, there is little load on the boiler, and the initial oxygen content of the inert gas may be high. If so, it is vented to the atmosphere up the mast riser while maintaining a back pressure. By this time, the valves and lines in the pump room have been checked. When the oxygen content of the inert gas is acceptable, the valve to the mast riser is closed and the inert gas directed into the full tanks. At this time, the discharge begins. It's good practice to start the discharge with a high pressure in the tanks. This makes it easier to keep up the pressure when the discharge begins. One of the first priorities is to discharge ashore any tank being used as a slop tank. Then, to reduce static electricity generation during crude washing, 2 meters from each tank to be used for washing must be discharged ashore. Oxygen readings must be taken in each tank before it is crude oil washed. IMCO regulations state that oxygen readings must be taken at the top and at half the ullage space in a tank. Since the atmosphere measured must be representative of the whole tank, readings from more than one point may be required. Before washing begins, float-type ullage gauges must be raised and secured. Once crude oil washing has begun, the system must be checked for leaks. Check that washing is taking place in the right tanks. Check the cycle times and operations of the machines. In the engine room and cargo control room, a keen eye must be kept on the IG oxygen level. If it starts to rise, action should be taken before the alarms sound. If the oxygen level rises above 8%, crude oil washing must be stopped immediately. The discharge will then certainly be delayed and may in some terminals have to be abandoned altogether. The cargo tanks must be maintained at positive pressure throughout the discharge. Check that the crude oil washing line is maintained at the right pressure during tank cleaning. The trim too must be checked to ensure that it will be right for the final bottom wash. It's necessary to ensure a safe keel clearance at all times. If a recycling technique is being used, the oil is returned to a holding tank. Guard against overflow of this tank. If using oil from the discharge line, ensure that the manifold pressure is adequate to drive the washing machines. Prolonged recycling reduces the solvent action of the crude and must be avoided. All the time that crude oil washing is taking place, a responsible person must be on deck, checking the system's operation and resetting the machines when necessary. If machines have detachable control units, IMCO regulations require that there must be sufficient control units so that each is only moved twice during a discharge. At the end of the operation, the crude oil washing line is drained back into the aftmost tank and all supply valves shut. Each tank is stripped again, sometime after washing has finished, thus allowing time for the oil to run down and across the tank bottom. The valves to the washing machines are closed and all cargo pumps, tanks and pipelines drained. The drainings are pumped to shore through a small line via the outboard side of the manifold. This final stripping is of the utmost importance. The whole object of crude oil washing is to reduce to a minimum the crude oil left on board. If the final stripping is not done effectively, a considerable amount of oil will remain on board and contaminate the ballast. Before a vessel can depart, the IMCO regulations concerning minimum draft requirements must be met. Firstly, the propeller must be totally immersed. Further to that, the trim must not be greater than 1.5% of the length of the vessel. These regulations determine the amount of ballast which will be taken in port. The ship's tables will reveal exactly how much. Usually, it will be more than the permanent ballast. Where local conditions require it, cargo tanks may have to be ballasted without venting any hydrocarbon vapor to the atmosphere. This can be achieved by simultaneous ballasting and cargo discharge, or by other methods acceptable to the local administration. These operations must only be carried out under the strict supervision of a senior officer because of the danger of over-pressurizing the tanks. Another consequence of discharging with inerted tanks is the necessity for closed ullaging. In addition to a fixed ullaging system, this vessel is provided with a bonded sonic tape capable of being fitted to any tank by means of a special vapor lock and valve. This method will give accurate and reliable ullage measurements, supplementing the readings from the fixed ullaging system. The ultimate criterion of successful crude oil washing is the measurement of the oil layer in the cargo tanks used for departure ballast. This must be no more than 0.085%. That's less than 1/1000th of the tank volume. Special equipment is needed to measure this oil layer. The device shown here is earthed to the tank hatch and lowered so that the middle of the instrument is below the interface. It is withdrawn and emptied into its accompanying perspex measuring cylinder. If there is any clingage on the outside of the instrument, ensure that this doesn't contaminate the sample. It must be allowed to settle until the oil and water have separated. Then the depth of the oil layer is measured. Reference to the instruments tables will give the volume of oil in the tank. An average of 3 observations is taken as the final result. One of the problems with crude oil washing machines, regardless of their make, is that frequently long periods elapse between their use. The machines must be checked during the ballast passage, with minor attention on the loaded voyage. This is the only way one can be reasonably certain that they will be working at the discharge port. If the control boxes are detachable, these must be stored and maintained separately. If a machine is found to be defective, then it must be repaired on the ballast passage. If necessary, the tank must be gas-freed and the machine taken out. A frequent problem is debris jamming the impeller or gearing, but occasionally more serious problems may develop. These machines are, in essence, comparatively simple mechanical devices, and it should be possible to rectify all but the most serious problems given close reference to the machine's maintenance manual. It is important to ensure that every washing machine is fully operational, for IMCO regulations have made crude oil washing a standard cargo handling operation. Spot checks can be made at any time, and if the amount of oil is found to be unacceptable, the consequences can be dire to both vessel and personnel. The golden rule is to understand what you are doing and to abide by the procedures laid down in the ship's crude oil washing manual. With experience, and above all, careful planning, ship's officers will find that they will be able to handle crude oil washing operations confidently and effectively. In doing so, they will benefit everyone involved in the transportation of crude oil and go a long way to preserving our environment.
Efficient cargo handling at loading and discharge ports is a critical area in the effective operation of a competitive tanker fleet. To help meet the demand for increased discharge rates, modern ships are fitted with powerful centrifugal pumps. But with the best pumping plant, consistently good results can only be achieved if ship staff have a basic appreciation of the characteristics and constraints of their particular system. Essentially, a centrifugal pump consists of an impeller wheel turning in a casing, with an inlet at the center or eye, and an outlet at the throat. When the pump's working, liquid from the inlet is spun round by guide vanes on the impeller and thrown outwards at high speed by centrifugal force. This acceleration creates low pressure at the eye, high pressure in the case, and a powerful flow of liquid through the pump. Pumps built for cargo work are sizable units, operating at hundreds of revs a minute and capable of shifting thousands of tons an hour. Ships normally have 3 or 4 of them, fitted as low as possible in a pump room between the cargo tanks and the engine room. Flow through a pump, as we saw, depends on various pressures. Low pressure at the inlet, high pressure developed in the pump, and whatever back pressures encountered en route. But pressures vary with the specific gravity of the liquid, so pump performance is best defined without reference to pressure, in units unaffected by specific gravity. These are the flow in cubic meters an hour against the resistance, head, in meters. To explain the significance of head, let's look at a simplified pumping diagram. Assuming an adequate supply on the suction side, flow in this situation depends on the impeller's speed and nothing else. But if the discharge pipe were vertical, of course flow would immediately be reduced by the effect of gravity. If we take a branch off low down, the reduction's minimal. Further up, it's worse. Up again, worse still. And so on, till eventually the effect of gravity stops the flow altogether. Now the height where this happens, the head, will be the same whatever we pump. The pressure at the base of the column varies with the specific gravity of the liquid. It varies appreciably between, say, seawater and kerosene, but the head remains constant for any liquid. We can show the relationship between head and flow on a straightforward graph. H for head, and the flow by Q for quantity. Starting from the bottom again, we measure the height of the first outlet, measure the flow, and plot the result. A low head and a good flow. Now we measure the next one. Measure its flow, and plot the result again. A greater head and a lesser flow. Now plot the next one, and the next one, to the maximum head, and the no flow state. Now, with the plots joined up, we have a performance, or HQ curve, for one pump at one given speed. Typical figures for a VLCC: 0 to 150 meters head, 0 to 5,000 cubic meters an hour for flow. But these curves apply to the pumps alone. They take no account of the inherent resistance within the ship. Frictional head losses in the lines, round bends and through valves, plus a mean figure for the lift to the deck. All these can be calculated, and from the results we can modify the pump figures to find the true performance curve after the resistance within the ship's been overcome. Obviously, we drop down the H-axis a bit now that some of the pump's potential's been used up negotiating the system. This new curve is the manifold curve. Each ship is supplied with a family of them, covering her range of pumps and pumping speeds. Manifold curves are the ones that really matter. They describe precisely the ship's capability during every discharge cycle. A proper understanding of their derivation and implications is fundamental to the intelligent use of cargo pumps. Manifold curves, then, give us a pumping profile for the ship, which stays the same wherever she goes. But the situation ashore differs widely from port to port. No two installations are alike, and each one presents its own resistance to a discharge. Back on our graph, we can see that the head ashore could be plotted on the same axes. Obviously this time, though, head increases with the flow, producing this sort of curve. The greater the flow, the greater the head. It may be a steep curve or a shallow one, but either way, where the shore curve intersects our manifold curve, shows us the best possible discharge rate for that particular ship at that particular port. During a discharge, control room instruments will give us an idea of the kind of shore curve we're pumping against. And of course, the sooner we know, the better. Take the question of how many pumps to run. This is a performance curve for 4 pumps, working in parallel. Reasonably, it suggests increasing the flow by an equal amount with each pump. 1, 2, 3, and 4. 4 times the flow. But in practice, this can never happen. If a shore curve, even a shallow one, is superimposed, we can see the diminishing throughput we get from each successive pump. And of course, the steeper the shore curve, the worse the effect. By the time it's here, for instance, there are really significant reductions. And in a case like this, there's little to be gained by running more than the first 2 pumps. This is a common experience regularly met in practice, and just one where the graphic information on performance curves can help you plan ahead before the actual discharge. Now for an example where we can prevent damage to the pumps themselves. A dangerous situation may arise if pumps are run in parallel but at different speeds, as quite a small drop in revs can produce a surprisingly large reduction in throughput. In this extreme case, pumps 1 and 2 are creating a head greater than the maximum possible for pump number 3 at its reduced speed. So if we run number 3 at that speed, there'll be no flow at all. It will still turn, of course, but all its energy will be converted to heat, and expensive damage can quickly result. So we have to remember that when pumps are running in parallel, there should be no variation in their individual speeds. Throughout any discharge, it's important to ensure a sufficient supply of cargo at the pump inlets. Our last curve alerts us to a potential danger here when the tanks are low. This is the curve for net positive suction head, NPSH. It shows us the minimum head of cargo necessary at the inlet for the pump to maintain suction. This head is a combination of the height of cargo in the discharging tank, plus any positive inert gas pressure on top. As the tank approaches draining condition, the available head tends toward the minimum required. And at this stage, cargo at the low-pressure inlet may begin to vaporize. When this happens, bubbles of hydrocarbon gas are drawn into the pump. We can see them properly in this cutaway model. Once inside the casing, the bubbles collapse under the high pressure and liquid rushes into the empty spaces. This effect's called cavitation, and it happens with such violence it actually erodes metal surfaces inside the pump. The results show up on this impeller, which in its worst places has been eaten right through. Warning of cavitation comes from the tachometers, which fluctuate wildly as the pumps start to lose suction. If this should happen, unless suction can be increased or the pump slowed down, discharge must be reduced immediately by partly closing the appropriate discharge valves. If we look at an NPSH and a manifold curve together, we can see how closing a discharge valve works. Suppose this were the situation. The minimum suction head necessary at the pump inlet now is here. So as soon as the available head falls below that line, cavitation will begin. But by partly closing the discharge valve, we can bring ourselves back to a new position on the NPSH curve, where the necessary minimum is just low enough again to resume a reduced but safe and steady flow. The significance of these performance curves can't be stressed too often. This elementary introduction seeks to give everyone concerned some insight to their importance in successful pumping practice. We've seen how centrifugal pumps work, looked at their potential on the manifold curves, the limiting effect of the shore curve, and considered a few of the implications on day-to-day operating. All the relevant information is available on every ship. Efficient cargo handling depends on its intelligent application.
Complex of girders, beams, steel, piping, and castings will soon become an oil tanker. More specifically, these compartments will become the cargo tanks of a VLCC, which is short for Very Large Crude Carrier. When it is completed, it will look very much like this VLCC. Its single purpose, its one reason for being, is to carry crude oil from the oil fields of the world to the refineries of the world, where it can be transformed into useful forms of energy. The energy users are all of us, a world population of consumers, with ever-growing appetites for gasoline, diesel fuel, heating oil, jet fuel, greases, motor oil. Name it, we use it. To do its job, the tanker must transport crude oil to the refinery and discharge it there at the lowest possible cost. To do its job, the tanker must transport its cargo safely and efficiently. And equally important, the tanker must transport and discharge the crude oil in an environmentally acceptable manner. To accomplish these objectives, VLCCs are constructed with the most advanced materials and techniques, such as automatic welding and use of quality-controlled prefabricated sections. VLCCs are outfitted with the most advanced navigational aids and cargo handling equipment. These pipes are part of a safety system on many VLCCs, which prevents the possibility of fire or explosion within the cargo tanks. Inert gases, usually exhaust gases from the ship's boilers, are scrubbed clean and then pumped through the pipes into the tanks. These inert gases replace the cargo, preventing oxygen from entering the tanks so that combustion cannot occur. VLCCs are manned by experienced crews who are kept up to date with continuing information and training programs. Today's VLCC practices the most advanced procedures in pollution control. During routine ballasting and tank washing operations, oil remaining in cargo tanks following discharge becomes mixed with seawater, and the industry has developed techniques to retain most of this oily residue on board ship for eventual discharge ashore. Seawater and oil make contact on board tankers because, unlike dry cargo and container ships, which often unload and pick up other cargo at the same port, VLCCs carry their oil cargo only one way. Loaded down with oil, tankers arrive at the discharge port, sitting deep in the water. As its cargo of crude is pumped ashore, the VLCC lightens and rises in the water. To maintain the necessary stability for control of the ship at sea without cargo, ballast in the form of seawater is pumped into some of the 10 to 15 now empty cargo tanks before the ship leaves port. So when the VLCC begins the return trip to pick up more cargo, these tanks contain water mixed with the crude oil residue remaining in the tanks. Before the vessel reaches the loading port, this dirty ballast must be removed from the tanks to make room for new cargo. Other tanks must be washed during the ballast passage so the ship can arrive at the loading port with clean ballast in the tanks. The conventional system of keeping oily tank washings and ballast residues on board ship is called load on top. It works like this. While the tanker is at sea, the dirty ballast is allowed to settle in the tanks until the oil separates and rises to the top. When the oil in the dirty ballast tanks has separated into layers of oil, oil-water emulsion, and water, most of the water is pumped out of the bottom of the tank. A layer of water is left on the bottom of the tank to be sure oily layers are not discharged to the sea. The oily residue then is transferred to a slop tank toward the stern of the tanker. At the same time, about 1/3 of the remaining tanks are washed. This is the control mechanism of a washing machine on deck. On most VLCCs, between 70 and 100 tank cleaning machines are permanently installed on deck so that the washing nozzles protrude into the tanks. Each tank may contain 5 to 10 machines, all connected to a permanent piping system. The washing machine, shown here operating in a test tank, sprays seawater against the top, sides, and bottom of the tank in a prearranged pattern, using force and flushing action to remove oil residues clinging to tank surfaces. These oily washing residues also are transferred to the slop tank. Seawater is taken into some of the wash tanks as ballast. This clean ballast can be discharged at the loading port without polluting harbor waters. In the slop tank, oily residues again are allowed to settle, with oily layers separating and rising to the top. The water at the bottom of the slop tank is carefully pumped into the sea, except for an ample layer of water below the oily layers. At the loading port, the new cargo of crude oil may be loaded right on top of the residue in the slop tank. Load on top is the technique presently used by a large proportion of the world's crude tanker fleet. It has reduced operational pollution to a small fraction of what it would be otherwise. Nevertheless, industry continues to research ways to further reduce operational pollution. The mechanical agitation of oil and water and transfer of oily washings to the slop tank during water washing forms oil-water emulsions, which are hard to separate and which may require special processing in the refinery. These oil-water emulsions also become part of the sludge which accumulates on tank surfaces. Sludge is a combination of the heavier components of crude oil, such as asphalts and waxes, which combine with sand, water, and mineral elements. In a VLCC of 250,000 deadweight tons, as much as 3,000 tons of sludge may accumulate during the 24 to 30-month period between dry dockings if the tanks are not properly cleaned. Sludge clogs drainage holes and piping and robs the tanker of valuable cargo-carrying space. Sludge must be removed by hand and requires special handling to avoid pollution. Crude oil residues left clinging to the tank walls and structure after discharge can amount to an additional 1,500 tons. Following load on top, most of the clingage from the washed tanks is transferred to the slop tank, but some remains, trapped by sludge. Finally, since load on top activities are carried out at sea, it is difficult to monitor the operation. Now, advances in tank washing procedures offer a new washing technique, crude oil washing. Crude oil washing is usually carried out not at sea, but while the cargo is being discharged at port. Washing with oil is not a new idea, but only recently have VLCCs been equipped to carry out the procedure efficiently and safely. Crude oil washing is usually practiced on VLCCs equipped with inert gas systems and permanently installed high-capacity washing machines, as in water washing. But some changes are made. Additional washing machines and more permanent piping are installed. Some newer machines are designed specifically for crude oil washing. The costs of converting an inerted VLCC from water washing to crude washing are modest compared with the advantages. The crew is specifically trained in crude washing methods. Here they are testing the tank atmosphere to be sure the inert gas system is doing its job. After discharge begins, part of the crude oil cargo is pumped back into the washing machines in the tanks and sprayed against tank walls and structure. Both the washing residues and the cargo are discharged together into the refinery storage tanks ashore. This laboratory simulation shows two steel plates covered with sludge from an actual tanker. One jet of water and another of Arabian light crude oil are aimed at the plates under equal pressure. Water washing is an attempt to scrub the resistant sludge away by force. Crude oil washing not only scrubs, but also dissolves the oil in sludge and disperses it to the rest of the cargo. To see the results of crude oil washing compared to water washing on an actual tanker, let's look inside two tanks on a VLCC. These construction scenes show two identical number 5 wing tanks. Similar tanks were filmed on one ship during one ballast passage. Before washing, both tanks contained a cargo of Iranian heavy crude oil. Both were washed for the same amount of time, at the same pressure, and in the same pattern. Only the washing medium differed. One was washed with water, the other with Iranian heavy crude oil. This is the interior of the tank that was washed with water. Sludge remains on many horizontal surfaces. Although much of the oil clinging to tank walls has been removed to the slop tank with the water washings, a significant amount remains, both on tank walls and trapped in sludge. To make this tank suitable for clean ballast, a more thorough water wash would be needed. This identical tank interior on the other side of the ship was washed with the Iranian heavy crude oil cargo. Tank walls are dry and completely free of clingage. Small amounts of sludge remain only in shadow areas where tank structures prevented the washing spray from hitting the residues directly. These results can be improved by repositioning the washing machines. Crude oil washing procedures now being used include a light water rinse at sea before clean ballast is loaded. The water rinse removes oil that may remain in pipes or in puddles that cannot be removed by existing drainage systems. Load-on-top procedures are used to collect rinse residues in the slop tank. The concentration of oil in water resulting from the rinse is low, since residues have been more efficiently removed by the original crude oil wash. Crude oil washing techniques are still being developed. Research indicates that with improved drainage systems, it should be possible to skip the water rinse, thus removing seawater entirely from the washing cycle. The aim is to be able to pump clean ballast water directly into a crude oil washed tank. Crude washing does mean more time in port, usually from 2 to 10 hours more. But its effectiveness in removing sludge saves much of the time needed later to prepare the ship for dry dock. In addition, the oily residues become part of the cargo and are refined with it into normal oil products. A regularly crude oil washed VLCC is able to deliver the same quality of cargo as a pipeline. The refinery receives more of the ship's cargo, and on each successive voyage, the ship can load a full cargo. Because crude washing is usually conducted in port instead of at sea, monitoring and inspection techniques can be developed to ensure both safe procedures and effective cleaning. A major change in how the tanks of the VLCC are cleaned has introduced a higher level of pollution control to crude oil transportation. The crude oil wash tanker is a cleaner ship. The crude oil wash tanker is a more economical ship. It increases the amount of cargo discharged. It saves time in removing sludge accumulation in preparation for dry dock.